Hi, my name is Carter Gowan. I'm from Boonville, Mississippi, and I research Ambrosia artemisifolia or common ragweed, its germination and growing rates, and its effects on different allelopathic plant species as a bioherbicidal substitute. Ambrosia artemisifolia is a weed. Pollen spreads rapidly in it. It causes conjunctivitis, asthma, and the like, and hay fever, causing allergenic discomfort for millions of Americans, or around it was around 7% of Americans. Um, it causes a lot of agricultural and economic damage as well. When grown in the vicinity of corn, it results in around 13% crop loss, and in the vicinity of soybeans, it results in around a 50% crop loss, resulting in a lot of around millions of dollars, even in the European Union alone, every year in just crop damage. It's a problem that's both locally in Mississippi, which is what for this year's project I wanted to focus on the Mississippi economy and the agricultural here, and both worldwide too. Most farmers use glyphosate, ALS inhibitors, atrazine, and the like, which are both hazardous to humans and the environment. It can cause neurodegenerative diseases, congenital diseases, cancers, and the like. For pregnant females, it can cause abnormal fetus development and preterm birth loss. Um, so that led me to wonder: is there a way that I can kill ragweed naturally using chemicals? So there is allopathic species that have been proven to reduce the growth of Parthenium hystophorus or Santa Maria feverfew. It's a broadleafed weed similar in structure and size to ragweed. So that was basically my basis for this project. My research question was, what are the allochemical influences against ragweed, and will they induce significant results by lessening either its growth or germination rates? My first hypothesis, or my null, states that there will be no visible relationship between the allochemicals or the allelopathic plants and ragweed, and any observable relationship between the two would indicate chance. An alternative hypothesis, on the other hand, states the opposite, that there will be a significant visible relationship between the allelopathic plant species and ragweed, and that the allelopathic plant species will lower both their growing and germination rates. For my data collection, I collected data every other day from soil level to the highest leaf or extremity, with the middle days being averaged in between. I recorded them in centimeters with a ruler, and only the tallest plant per pod was averaged, not the average of how many were grown. The control for this project was the common ragweed by itself, and 40 plants were grown in a tray, and there's a graph on the next page, which I'll get to. And for the independent variables, I tested 9 different allelopathic plant species: sorghum, winter rye, upland rice, blue grama grass, mammoth sunflower, French marigold, sensitive plant, eucalyptus, and buckwheat. And then, like I mentioned before, the plant height was measured in centimeters. This is the graph right here. That's basically a prototype, or basically a model for the allelopathic plant species tray alongside the ragweed. So the double A is Ambrosia artemisifolia, or the ragweed. So I planted those every other rows in rows of 5. In the middle rows were the allelopathic plant species, or in this example, the Sisali cereale, the winter rye. Um, I placed these under a 12-hour growing photo period, under LED lights. I used filtered water to water every other day, the same day that I measured. I used humidity domes as well to expedite the growing process and to keep everything as controlled as possible. Later in the project, I used a spectrophotometer to identify and quantify certain pigments such as chlorophyll A, B, carotenoids, and anthocyanins. These all, if they were high or low, would indicate plant stress and nutrient deficiency, how stressed out the plant is, and the ROS, or the reactive oxygen species levels. Basically, how fast the plant's metabolism is. And these are the pictures of the 4 sorghum bicolor right here on days 10, 15, 30, and 40, and 50, excuse me. Um, and this is my ANCOVA test, basically for my statistical data. For the species interaction, X plus Z at the bottom, with a p-value of less than 100th, there was extreme confidence that the sorghum bicolor did limit the growth of Ambrosia artemisifolia when exposed to it. When the Ambrosia artemisifolia was grown alongside the sorghum color, it produced only a 55% germination rate, or around 20% less than the advertised germination rate of around 74. The earliest recorded day of germination for the Ambrosia artemisifolia was day 6, but the earliest recorded day of the sorghum's growth was on day 3. The Ambrosia artemisifolia measured around 2 centimeters measured 2 centimeters lower grown alongside the sorghum rather than the control. The Ambrosia artemisifolia sorghum tray recorded a germination of around 95%, which is significantly higher than the advertised germination rate, and it was around 14.4 centimeters, while the mean was around 10 centimeters. In terms of my spectrophotometry, let me zoom in. I guess it's all right. To the left, it's the Ambrosia artemisifolia grown alongside the sorghum. And as you can see in the carotenoid chart, measured at around 470 nanometers and absorbency units. The Ambrosia artemisifolia grown alongside the sorghum measured around 0.8 absorbency units lower per concentration, and which indicates high ROS levels, which indicates the plant is not metabolizing fast, essentially meaning that it's dying due to the intense oxidative stress due to the biotic stresses of the sorghum against the Ambrosia artemisifolia. In terms of quantitative data, sorghum bicolor influence ragweed had a shorter average root length. I did this in a random pods that I took measures from. It had a lighter average fresh weight, and the results implied that it does regulate growth and germination rates. In terms of the spectrophotometry, the control measured higher in all 4 assays than the sorghum influenced ragweed in both chlorophyll A, B, carotenoids, and anthocyanins, defining the biotic stresses that it underwent from the allelopathic plants. This project provides a bioherbicidal substitute to the widely used hazardous herbicides. It's preventing health effects and biodiversity loss, and it saves farmers up to 80% in cost than traditional herbicides. But most importantly, this project could relieve countless individuals suffering from hay fever, conjunctivitis, asthma, and the other side effects that come along with ragweed's intense pollen season. And that's it.